Hello everyone, in this video we will be learning about the principle on latent heat and phase change material. As we've briefly discussed on our previous video for the psychrometric chart, the heat can be divided into sensible and latent heat. Most of you are already familiar with the sensible heat. A sensible heat is generated by a random motion of molecules, and the temperatures that we know is a measure of the intensity of this motion. As you can see in this case of cold water, the water molecule is moving slowly because the low amount of heat it contains now. But as we apply heat energy into this, the temperature of the water starts to increase. The rise of the temperature is equal to the increased motion of its water molecule. As long as water is maintaining its form of liquidity, the rise of temperature, which is again same as the motion of its molecule, increase proportionately to the amount of heat that is being applied. When the temperature reaches a certain degree, in case of water 100 degrees Celsius, its molecule starts to change its form of structure. During this time of transformation, a further energy input is used to break the bond of water molecule, and therefore it does not increase the motion of the individual molecule. During this period of phase change, the temperature stays the same despite the continuation of energy input. This energy instead is stored as a form of changed phase, and we call this as a stored latent heat energy. When we think of magnitude it takes to break this molecule structure and changing the phase of the material, it is quite a lot relative to the energy it takes to increase the sensible heat. In case of water, notice in here that it takes only a 2.1 joule to increase the 1 gram of ice temperature 1 degree Celsius higher. It takes 334 joule to melt the ice while and change its phase to a volume of water. The boiling phase takes even more latent heat for its phase change. As you can see here, it takes 2260 joule to evaporate the 100-degree water into a form of steam, while the temperature does not change during this time. This is why you feel very cool when the sweat from your skin evaporates as the cool and dry breeze blows by. As the water evaporates from your skin, it takes away incredible amount of heat energy around this molecule and make your skin surface cooler than its surrounding temperature. When you are melting an ice cube with your finger, as water changes phase from solid to liquid, it takes a large amount of energy around it, and your finger feels much more coldness compared to touching something solid that has similar coldness to it. We also utilize the phase change when we steam something. When the air full of steam touch on objects such as an eggshell, as the steam changes phase from vapor back into water molecule on the surface of the egg, this time it releases large amount of heat energy, making the surface of the eggshell much more hotter than placing the same egg on the same heated air that has the same sensible temperature but without steam in it. This phenomenon of phase change is property that can be found in a lot of materials. And based on the material specific temperature it takes to change its form, which is unique to that material, we can utilize that material to our benefit for heating and cooling, especially for outdoor activities. You are maybe probably familiar with these cool packs and cool jacket that usually come with a stimulating button that starts the phase changing process whenever the user needs to start the phase changing process. One of the biggest challenge we face when we design a building is to control the interior temperature against the harsh temperature swing of the outside air. Using and locating the material that can store the heat energy is the most useful and easy way of achieving this passively controlled building design. Although we will talk more about this design strategy further in the later portion of our class, as you can see from this graph, the impact of the diurnal change of the temperature swing can be reduced by the use of thermal mass inside the building. And as you can see that the use of material with a higher thermal storage capacity will achieve this purpose in a more powerful way. Among the commonly used conventional material with thermal heat storage capacity, you can see that water has the most amount of heat storage performance, followed by a concrete and brick material. However, if we use the latent heat storage phenomena through the use of PCM, this heat storage performance value can well surpass this traditional material, only if we can find a reliable way of its use and overcome its cost. In order for us to control the indoor environment through the phase change material, we need a material with the phase change occurring near our comfort zone. Therefore, from this graph, you can find that the use of paraffin and the salt hydrate is the right material for us to use for our building design. And indeed, these are mostly used phase change material for our construction industry. Some buildings, such as the Melbourne City Council building CH2, uses a centralized indirect method, which cools and distributes water through that is cooled by PCM, which is located at the basement of the building, and distribute the cooled water throughout the building in order to operate the chill beams, which end up cooling the interior space. On the other hand, for the most of the smaller and residential application, the PCM material is directly applied inside the interior partition, hidden behind the gypsum wall, providing a heating and cooling capacity, and this is considered to be an efficient and passive building design strategy.